Hi, everybody. I wanted to kind of walk you through our climate change PowerPoint because there's so many great things in here. So it's long. And since you don't have to write any notes, I thought that at least I would explain it to you because there's a lot of juicy things in here that I wanted to talk to you about. So this PowerPoint is also posted in your Schoology independently, so you won't have to listen to me. But I see I'm here in the corner. Hi. I don't even know if I can move myself. Oh, I can, look. Okay. Anyway, I'll make myself as small as possible. Okay, so global climate change. I've been waiting all semester for this. So I love this quote. We warn you that unless you act quickly and decisively, our homeland and others like it will disappear beneath the rising sea before the end of this century. That was spoken less than a decade ago by Mohammed Nasheed. He's the former president of the Maldives. So where is the Maldives? That's my question to you. Here we go. So the atmosphere. The atmosphere is a thin layer of gases that surround the Earth. We've talked about this. This is what we spent, I think, in the beginning of the semester. We briefly talked about the atmosphere and the different layers. We live in the troposphere, which is the first layer of the Earth. And in your front page of your reference tables, you will see troposphere, and I'll tell you the different gases that are in it. So the troposphere is what layer contains the water vapor, and that's what's important to us because we need water to survive. So the atmosphere is mainly nitrogen, oxygen, and a little bit of argon, 0.93%. So if you look at the little graph right there, you see it's mainly nitrogen, oxygen. So oxygen is what we breathe. Nitrogen is most of the atmosphere. So what are the other parts? What's this greenhouse gas that we talk about? So water vapor, carbon dioxide, methane, nitrous oxide, ozone, and CFCs. And CFCs stand for chlorofluorocarbons. That's just kind of fun to say. Say it with me. Chlorofluorocarbons. Anyway, so those are the different types of variable gases that are found in the atmosphere. What's the greenhouse effect? The greenhouse effect in and of itself is not bad. It's because of the greenhouse effect why we actually have life here on Earth. So the air absorbs and then re-radiates some of that heat back down to the Earth. So I kept this super simple because I just want to give you a little backstory and background on this. There's obviously a lot more in depth I can go about the greenhouse effect, but I at least wanted to bring your mind back around it to know what it is. So greenhouse gases include carbon dioxide, CO2, methane, nitrous oxide, and those chlorofluorocarbons, CFCs. The greenhouse effect keeps the Earth's temperature within a habitable between a range that we can live in. So, for example, could we live on Mars? Short answer, no. Mars has a thinner atmosphere with no greenhouse effect. There's other reasons too why living on Mars would be hard. Someday you pull this up from YouTube in 1,000 years from now, be like, here we are on Mars. This Mitchell was wrong. Well, yeah, that's totally possible. But in general, no. Because there's no real substantial air there, so there's no greenhouse effect. So a Martian summer, daytime could be close to 70 degrees Fahrenheit. That sounds lovely. However, at nighttime, everything just whoosh, all the heat goes back out into the into the universe, and at night it would be below 100 degrees Fahrenheit, cold. So the Earth's atmosphere has undergone many changes throughout its geologic history. Hence why we talk about geologic history first. And if you went through the Earth Viewer app, there is evidence of these different things. You could go back through it, and I had an activity I wanted to show you because it's really cool, but unfortunately I don't think we're going to get to it today. It makes me sad. So at least let's kind of sum this up. So the pre-Cambrian period, remember pre means before, Cambrian, if you recall from geologic time a couple weeks ago, is life. So pre-life, well, there were some things, blah, blah, blah. That was 4.6 billion years to about 540 million years ago, give or take half a year. The Earth's atmosphere was mostly carbon dioxide and nitrogen. So what changed? There were these small species called prokaryotes, and a new life called cyanobacteria evolved the ability to do and to perform photosynthesis. So think back to biology, think of what photosynthesis is. And so it absorbed the carbon dioxide and it gave off or released the oxygen. So slowly over time, it ended up having more oxygen put into our atmosphere, which is what we know and love today. So the picture I have here is from Lake Erie. This is not from the Precambrian period, just saying, not that old. So photosynthesis weakened the greenhouse effect because it continued to remove carbon dioxide and the oxidation of methane. So this triggered the first and longest ice age ever faced up until even currently by the Earth. This was called the snowball Earth. So it was this weird thing. They don't have much evidence of it because it was so freakishly long ago, but there is some evidence to support that it happens. That's why it's called a hypothesis. So the snowball Earth hypothesis suggested the planet was mostly completely covered with ice. If you go back through your Earth viewer, you will see this in the Precambrian. It's actually kind of cool. So ice ages. So an ice age is a period of time where the Earth's surface temperature is low enough that glaciers form at the poles, high latitudes like top and bottom of the Earth, and in the mountainous areas. So we have experienced at least 5 major ice ages. So here's a chart that shows the ice ages from the past 2.4 billion years. So remember, the Earth is 4.6 billion years. So this is about a little less than half of Earth's lifespan. So if you look all the way to the right, today you see that we look like we're coming out of an ice age, and you're like, well, then why is it warming? We'll get to that. Way back in time, about 350 to 260 million years ago, our timeline is not to scale, there was the last major ice age, and then there were 3 prior to that. So during glacial, or I like to say glacial, I don't know why, periods, years at a time when it stays cold, glaciers are advancing and retreating. So during growing and retreating, growing and advancing, during interglacial periods, do you miss me? The overall climate is warmer, leading to the glaciers to retreat. We are currently, like I said last slide, in an interglacial period of an ice age. So hard to say, not hard to figure out. So if you look at our chart with this one, we see temperature on the left-hand side, and years ago on our x-axis, and all the way to the right, you see how our temperature is above the line that is indicating between glacier and interglacier. So we are just emerging from a glacial period. So, but you're like, I don't remember it being so cold when I was little. Remember, this is geologic time. We got these huge spans of time. So compared to you and I, it seems like a long time ago, but compared to the geologic history, it was just a little hot moment ago. So proxy, what's a proxy? A proxy is basically an indirect measurement. So we've talked about this. Remember in the beginning of the year, we talked about observations and inferences and how they lead to predictions and hypotheses and etc. So how do we know all this stuff? Well, based on the measurements that we take, we can lead to inferences about other things. Remember, we talked about how do we know that the outer core is liquid? How do we know that the inner core is solid? Well, based on our other indirect measurements, even though we've not even dug through even the crust, we still have pretty concrete body of evidence to support that the outer core is indeed liquid. Okay, so back to proxy. So this is the same foundation of how we know why the climate has shifted and what's currently happening by all this collection of data that we've been gathering. So a proxy, an indirect measurement. So we use these indirect measurements to figure out the temperature. Oh, there's a typo. Do you miss me? Since we weren't there, I should put a little C in there. So we do what's called an ice core. So we drill into the ice in the Arctic that hasn't melted for a long, long time, and we can pull out these giant ice cores, like in this picture. That is not me. I wish it was. It'd be so fun to do. Wow, that'd be so fun to do. I'll have to look into that. Anyway, so we pull out these giant ice cores, and then we look at the dissolved bubbles that are frozen in time of that ice. You can see the dissolved bubbles of atmosphere in each layer are analyzed. So moving on, we can gather 2 different things, 2 sets of data from studying the core. So we gather the temperature. How do we gather the temperature from this ice core? by calculating the relative amounts of oxygen isotopes present in the water and ice. So do you remember in chemistry, if you took chemistry, you remember something that's called an isotope. An isotope is a variation of our atoms and of the, think of the elements, so think of the periodic table. If you're like, I didn't take chemistry, it's fine. Let's just, you know, for time purposes, let's just say that they can calculate based on the isotopes. And then you learn all about it in chemistry. So how much greenhouse gases are in the air is the second thing we can figure out. So we can figure out the temperature, and we can figure out how many greenhouse gases. Oh, Jenny's home. Do you even see that? That's really funny. How much greenhouse gases were in the air? How? By pulling out the air from the air bubbles that are frozen in the ice. So they take in thin little needles, they extract the air that's been frozen in time from millennia ago, and they analyze that information. They can tell what greenhouse gases were in the atmosphere from that time that's been frozen in ice all that many years ago. Isn't that crazy? Anyway, I love this stuff. Okay, so here's a big chart showing that. So the top one has our carbon dioxide, CO2 concentration. ppm means parts per million, and how many years before present, because it's all about us, so it's all based on before now. So it starts on 0 all the way to the right and goes back in time as you go to the left to about 400 million or 400,000 years ago. So based on this information, you can see that all this stuff, how the carbon dioxide has ebbed and flowed, but if you look currently all the way to the right, see how it's shooting up. Oh wait, let me move my little head. Can I? So see how this is increasing exponentially? That's not necessarily a really good thing. So things have shifted, yes. So we go down, we go up, we go down, we go up. But to this point here, notice the angle of our curve, so much of a higher degree. And 25,000 years before present, we see a spike in our temperature and also a spike in our methane. So that would be interesting to figure out what was happening then. And so now we also have a spike happening here, and that correlates with the methane also increasing. So I'm giving you a super basic overview. There's a lot of in-depth in studying with this, but I thought I'm still diving in a little bit deeper because it's really important stuff, because it's in the news everywhere. So if you have a foundation of what they're actually talking about, it's so helpful. Okay, the last glacial period on Earth ended about 10 to 20,000 years ago. The overall temperature has been stable since, a few exceptions triggered by natural phenomena, and we'll get to that in a second. So here we look at our years, quasi-log scale. Do you remember what a log scale is, a logarithmic scale? I'm not going to get into it and confuse you, but some of you are like, oh yeah, I remember. Exactly. So we have deviation, which means the change in temperatures from global average. So basically, if it's negative, it's changing in one direction. If it's above, it's changing in a different direction. If it's right on 0, that means that the temperature average has not changed. So it's a little bit different than a normal temperature scale. So basically what we're seeing is that there's big changes at the end of our last ice age. We're relatively stable during the Holocene, a little bit of a shift in our medieval warming, a little bit of a downshift in our little ice age, and then 21st century increases. So this graph is from a little bit, it says 2009, it's from 2012, I believe. Might be earlier. Anyway, so, but there definitely is a progression showing that our temperature deviation, our temperature change has increased towards getting warmer. So all that I'm talking about now is to support, how do we know the climate is changing? Is it actually changing? Is it just something that I picked up in the National Enquirer? My grandma loves the National Enquirer. It's hilarious. She's like, it's true, Julie's right here. It's not true, Grandma. I'm sorry. I love you, Grandma, if you're watching this, if you can figure out YouTube, but it's not a real newspaper. Anyway, why did I say that? I forgot. Okay, medieval warming and little ice age. The medieval warm period lasted between 950 to 1250 CE. You history buffs know what CE is. I'm not going to pretend and say the wrong thing, so I'm just going to plow through. With warmth in some regions exceeding the current post-industrial era, and that's what we're in now. So it was warmer than it is now. So how do we know this? Historical events, things were happening at the time. The Vikings crossed the ice-free seas and colonized Greenland and Newfoundland. There are high crop yields, meaning that there's a lot of really delicious stuff to eat that was grown from the ground, and economic prosperity throughout much of Europe and Asia. So great things. The Little Ice Age, that was a period of cooling that lasted from the 16th to 19th century. So 16th, 17th, 18th, 19th, so about 400 years. So the Viking colonies in Greenland failed and were abandoned. North American Indian tribes formed alliances in response to food shortages. So these are all different events that we know that supported the evidence that there was a Little Ice Age. The river Thames frequently froze over the winter, leading to frost fairs. So at least they did something positive with that. You can see that picture from the Frost Fair. I like that name, the Frost Fair. A strait called the Great Belt froze over, allowing Sweden to march across it and invade Denmark. Oh, bummer for Denmark. Yes, there are natural causes of climate change. Of course there are. So here are 3 different things. Wow, bad spelling. I forgot to check that. The Milankovitch cycles, volcanic eruptions, and the ocean current. Oh, I'm so embarrassed for myself. 1, the Earth periodically undergoes a series of changes called the Milankovitch cycles that affect the amount of global sunshine, solar radiation. So these are things that naturally occur in a natural set pattern. So there's 3 things that classify as a cycle. There is the shape of the orbit. So the Earth goes around the sun in what's called an ellipse. It's not quite a circle. Circle, it's a little bit more of an ellipse, kind of like an oval. It pretty much looks like a circle. It's close enough to a circle, but it's technically, mathematically, an ellipse. So the shape of the orbit shifts about every 100,000 years. The tilt of the axis, how much are we tilted? 23.5 degrees. That hasn't always been the change. Sometimes it hasn't always been the same. Sometimes it tilts a little bit more. Sometimes it tilts a little bit less. So that change can affect those direct sunlight rays, and it can affect the global temperatures of the Earth. The third reason of the cycle could be the wobbling of the Earth's axis. So think of a top. You know, when you spin a top, it's like whoosh, and then as it slows down, it starts to wobble. And it's that wobbling where that shifts the axis tilt, that changes where the sunlight is directly hitting, maybe north of the equator, south of the equator. It's tied into the tilt of the axis, but suffice to say, the Earth wobbles. So these are natural occurrences. It's nothing that seems to affect us in our lifetime because we're here for like, I mean, my grandma's 94, she's still kicking it. So we're here for like 100 years if we're lucky, right? So if the shape of the orbit is every 100,000 years, we're not going to notice any teeny tiny shift in our lifetime or even in our ancestors' lifetimes. So here's a very fancy graph that I just love the graph. So I'm going to geek out, look at it for a moment. Now I'm going to move on. Okay, number 2, what else is natural? Volcanic eruptions. They release sulfur dioxide and smaller particles called particulates that scatter solar radiation, causing a cooling effect. Example, in 1816, Mount Tambora in Indonesia erupted, causes snow to fall in June in North America. Can you imagine? Resulting in crop losses and food shortages. It wasn't the best year ever. So another reason is the Great Ocean Conveyor Belt. So in your reference tables, we didn't get to it, but you can pull it out and you can flip through, and there's the map of the world, and it shows the ocean currents, and there's a line that shows warm currents and a line that shows cool currents. And so the gist of it is warm air rises, warm water rises because it's less dense. And when it gets colder, it sinks because it's more dense. And so this natural convection current cycle is what drives the entire ocean movement. So this is what keeps our climate a little more consistent. So this is called the Great Ocean Conveyor Belt. It's an underwater current made of the mixing of warm and cold salt water. However, you can start to really mess up this conveyor belt because if you add fresh water to salt water, you're going to change the density. If you've ever went and floated in the Great Sea, or if you've ever floated in Salt Lake by Salt Lake City, Utah, you will notice that you are a lot more buoyant, meaning that you float more. And the reason why you float more is because the water itself is more dense, because salt water is more dense than fresh water. So if you add fresh water into this mix, by the melting of our glaciers, and you're going to shift this whole natural conveyor belt. So for example, in general, what happens, warm currents keep Western Europe warmer than other areas in the same latitude. So look at the picture I have. Look over there by Norway and Sweden, Denmark, and you can see that warm Atlantic coast current coming up. It also warms up Ireland, Scotland, England, but that's comparatively, if you look along the latitude, oh, I think I can do this, over here, that's the same latitude as northern Canada, and they're not known for their super warmness. So that's because we have that cold current coming down here, which keeps it even cooler. So moving on. So if the climate changes naturally, then why are scientists saying it's caused by humans? Well, here's evidence of climate change. Okay, we're gonna get to the human thing in a little bit, but first I wanna just at least showcase why the climate is actually changing. Step one, figure out if it's actually changing. Don't take my word for it. Let's figure out, let's look at the data. Since 1958, daily measurements of atmospheric carbon dioxide levels have been taken at an observatory on Hawaii. Hawaii was chosen to avoid the influence of large forests or cities because they can change the climate. So Mauna Loa Observatory, there's a picture of that. So what do you think they found? Here are the results. Carbon dioxide levels fluctuate within each year. They go up and down, which makes sense, depending on the season of the Northern Hemisphere. So a little bit higher in the winter, a little bit lower in the summer. So since the measurements started, carbon dioxide has been increasing at Mauna Loa. So if you look at the graph from 1960 all the way up towards 2020, you can see that it's been increasing a lot. Okay, well, what do we do with this data? Gather more evidence to see if it's just Hawaii a strange spot of carbon dioxide increasing, or is this something that happens around the world? Oh, seriously, this is so fun and embarrassing, all my typos. In 1988, the United Nations set up the Intergovernmental Panel on Climate Change, the IPCC, to figure out or assess climate change. So their mission was to gather evidence that's taking place, to assess and to summarize the impacts and the future risks, to provide options for adapting and mitigating its effects. So the results. According to the IPCC 2014 report, quote, warming of the climate system is unequivocal, as it is now evident from observations of increases in global average air and ocean temperatures, widespread melting of snow and ice, and rising global average sea level. Wait, what was on that last slide? From 1988 to 2012, the panel set up by the United Nations measured if climate change was happening. The answer in 2014 is yes. Climate change is happening. Our world is currently warming. So if someone's like, it's not happening, then you just very kindly say, your data is just before 2014. The data concludes pretty unequivocally or pretty much true that it is happening. So how do we know this? Well, there's lots of things we know that supported them making this statement. The temperatures are rising. That makes sense. So they've been taking the land and ocean surface temperatures. They've increased since the Industrial Revolution. There has been 0.9 degrees Celsius increase. I think that's actually more since this was originally created. 19 out of 20 of the warmest years since 1980 have occurred since 2001. The area of greatest warming has been in the Arctic. So there's my picture. Number 2, the ice sheets are melting. I'll let you read this on your own. Number 3, sea levels are rising. Sea level worldwide is increasing primarily due to 2 factors. 1, you have the water flowing in for the melting ice sheets, so you're literally increasing the quantity of water, but also there's something called thermal expansion. It's the tendency of water to expand in volume as it warms. So do you remember when I told you about my balloon friend? Is this really going on YouTube? So the balloon friend, I have a little friend, and then he he kind of, before Fred met his balloon demise, he expanded because as you heat something up, it expands. That's all I'll say about that. So, well, I can hear you guys. Mitchell, I like warmer weather and I don't live near the ocean, so why should I even care? How will this affect me? I say there are several impacts of climate change. So the growing season is changing. The increase in surface temperature has many aspects of plant growing season. So if any of you guys are agriculture, some of you guys are farmers yourselves, or you have family members that are farmers, and you can talk to them about how this has shifted and how this has changed. Or the next time when you're able to go out and you're talking with your local produce person who is your farmer, you can ask them, how has your business shifted in the past 10, 20 years? They'll tell you. So another reason, the range of many pest insects are increasing. So mosquitoes that spread diseases like malaria and West Nile virus have expanded their ranges. And the big one that we know in Colorado is the pine bark beetles. You head up into the mountains and you can see the devastation caused by the bark beetle forest destruction. And they're a natural species, the pine bark beetle, but not here. So what usually kills it is a really hard, cold, deep, frozen, sustained temperature in the winter. And we just simply haven't had that. So that's begun to infest and impact our Rocky Mountain forests. The coral reefs are dying. Coral bleaching occurs when coral polyps eject the symbiotic algae into them with stressful environment conditions. And so you have the coral bleaching. I think the next slide is the sad one. No, well, this is sad. You'll see. There are more hurricanes, more storms, more hurricanes, more death and destructions, more impact on our economy. We're losing sea ice, which is causing polar bears to die. I'm going to move on because I cannot handle that picture. It just breaks my heart. Our glaciers are melting, which affects fresh water. Any of you, when you turn on your faucet, ever wonder, where is this fresh water coming from? Yes, it comes from the Erie system, but where do they get the water? Most of our water comes from the reservoirs up in Demdare Hills, up in the Rocky Mountains, and the water from the reservoirs comes from the melting of the snowpack. So if we have a low snowpack season, we are going to not have as much water in our reservoirs and we're going to head into a drought. So these are things that affect us. So if we don't have a lot of snow, a high snowpack in our mountains, then it's going to result in that summer not having reservoirs filled. So this is a huge impact for us. So this picture I thought was cool. It's an 1870 postcard that kind of shows where the glacier was. And then you look at the picture now and you're like, where's the glacier? Melted. The Himalayan glaciers are also declining. What else, Mitchell? Welp. So here's a little bit of review. Hydraulic cycle, remember 6th grade. So it describes the movement of water through evaporation, precipitation, runoff, and infiltration. The phase changes of water in this cycle are driven by heat. So you have more heat in the atmosphere as that whole domino effect, a higher rate of evaporation from land and sea, and both, well, that's land and sea both. You have a higher rate of evaporation from land and from the sea, and you have a greater capacity of the atmosphere for holding more moisture. So that could be good, that could be bad. Remember, this is called climate change. It's not called climate bad. Why is it called climate change now instead of global warming? Because climate change has a paradoxical effect of increasing the rate of both drought and heavy precipitation events. So change is because it changes what has currently historically for at least our human brain's time span. It changes it from that. So we have more precipitation in some places. We have less precipitation in other places. We can even see that a little bit, and you've heard about this in our area in Colorado. Talk to your elders. If your grandparents had grown up around here, ask them what it was like even just 50 years ago. If you still have your grandparents around, and even if they didn't grow up in Colorado, ask them what it was like wherever they grew up and what changes have they seen even in their lifetime. So that's the thing. Like I've been saying that, geologic time is so big and so long, and it's hard to wrap our human brains around it. But what's frightening is that there is a shift and a change that's happening so rapidly, so exponentially, that we, in our lifetime, we are experiencing it and we are witnessing it and we are seeing the effects and feeling the effects from it. And that, my friends, is what makes this something that we should really care about. Back to what I was saying. So as ocean level rises, the coastal cities become more of a risk. So erosion of beaches and shorelines, flooding, damage of storm surges. So there's a picture of the Maldives. I apparently was on the Maldives terrain for a little while. I kept putting pictures of that in here. Okay, so does the scientific community really think, after all this slides, really think that climate change is happening? Yes, 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 they do. So here are the different organizations that have endorsed this position that yes, indeed, the climate is changing. So all those. If you feel it's appropriate, check with your people at home first. I don't want to have you watch something that you really shouldn't be watching, but this is a link for a little John Oliver clip. He kind of shows in his John Oliver way when they say 97% of scientists say that climate change is occurring. So watch that. It's funny. You don't have to watch it, especially if you're like, I hate John Oliver. Then don't watch it. It's no big deal. Okay, solutions. Now that you're depressed, all is not lost. There's lots we can do to stop and shift and change and mitigate climate change. We can do mitigation, spelled wrong too. Really, Mitchell, before you start recording these things, maybe you should spell check. Geoengineering, it's similar to geoengineering, but different. I'm embarrassed. And legislation. So mitigation, basically, we need to keep our forests around. We need to keep our oceans healthy so they have the carbon dioxide, have places to go and to stay cornered up. Carbon dioxide is one of the biggest things. So what rock does carbon exist in a lot? Coal, limestone. So if we're burning coal, we're taking that carbon that was locked in this rock and we're releasing it into the atmosphere. If we take limestone and crush it up and make it into cement, and all the particulates are going into the air, interesting. Shifting our society. So reduce greenhouse gas emissions. So for example, there's been talk about switching from fossil fuels to renewable energy sources. We have solar panels on our high school. Do you guys know that? We could consume less beef. I was letting you guys yell at me for a minute. Okay, I think you're done. Yeah, you consume less beef. Cows release large amounts of methane. I'm not saying you have to do this. These are just some things that one could do. We can find alternatives to ammonium fertilizer. So fertilizer, when we go fertilize our lawns, we could shift to something more natural instead of adding more nitrogen, which makes nitrogen oxide, which is a greenhouse effect or a greenhouse gas, and adding that into our atmosphere. So all these are like little teeny tiny things that add up to a big cumulative effect. Geoengineering, a lot of different things, solar radiation management, carbon capture storage, and legislation. If you're interested, you can go back to the slideshow or hit pause to read these tweets. This kind of goes with, in the beginning of the semester when we talked about the difference between climate and temperature. Global warming. So here are things that we can prevent, and here are things that we can clean up. Okay, so after 55 slides, okay, hi Mitchell, the climate's changing. But the million-dollar question is this climate change caused by humans? So your assignment will be to tell me, what do you think? And of course, the next time or the next assignment, I'll answer that question or have you do some research to figure it out. Okay, I'm done.